So in this, the second part of the 9th lecture, we're going to look at the superconducting wave function that comes from BCS theory. And we'll look and see how that can be used to predict and explain some of the properties of superconductors, for example, the Meissner effect. Okay, so to summarize some things about the Cooper pair. So the Cooper pair, the electrons, the two electrons in the Cooper pair have opposite momentum. So in their ground state, they're at rest. They have no net momentum. And they are of opposite spin. So we have an up spin coupled with a down spin electron. This means that the Cooper pair has no net spin and no net angular momentum. Okay. The first of those is no net spin is always the case. The second one is certainly the case in most conventional superconductors. And that means that the Cooper pair is what we call a composite boson. So we remember that fundamental particles can be described as either fermions, so things that have spin 1/2, for example, or bosons, particles that have integer spin 0 or 1, for example. So the Cooper pair is what we would call a composite boson. So it's not a fundamental particle, it's something comprised of two fundamental particles. But it is a boson. Okay. Now you're more familiar, I think, with dealing with fermions because that's what we were doing in the whole electronic properties of solids course. When we're understanding, the free electron gas, for example, the electrons there are fermions. The Pauli exclusion principle says that each fermion has to have its own unique set of quantum numbers. But the point with bosons is that in the ground state, there's no restriction. There's no equivalent to the Pauli exclusion principle. Each Cooper pair can have exactly the same quantum numbers, okay, and it can be in exactly the same quantum state. This is really important. Okay, so and in fact, the binding energy of the Cooper pairs, we saw it's cooperative, so it's actually greatest when everything is in, all the Cooper pairs are in the identical state. Okay. Sometimes you might read about this being termed a macroscopic quantum state because there's just one quantum state for the whole system. Now, this actually presents us with a considerable simplification. The wave function for a fermion system is what we would call a many-body wave function. Okay, you often see this term many-body because it's actually super complicated to write down and to calculate. When you go on next year and we do the intro to modeling course and we look at something called density functional theory, we'll see that there are some tricks that enable us to avoid doing calculations in terms of this many-body wave function, because just even writing it down for more than 10 electrons is almost impossible. It's really complicated. So we do some simplifications there. But so for fermions, the wave function is super complicated. Bosons, at least in this condensed state where they all have the same quantum numbers, is really much more simple, because the fermionic wave function has to depend on the coordinates of every possible electron in the system, and there are a lot of electrons in a macroscopic system. But the boson wave function is the same for all the particles. So the boson wave function can be written really quite simply as just a function of R. Okay. And it's that we're going to look at. So BCS sort of says that we can take this more simplified wave function, this boson wave function like this, and we could form, for example, a pair concentration. So the mod squared of this wave function gives us the concentration of the Cooper pairs. Now, if we make the assumption that n is uniform, okay, so let's imagine that we've got a uniform concentration of Cooper pairs in the material. It seems a reasonable first approximation to make in a metal. Then we can write down the wave function. We can just take the square root of this equation, And what we end up with is it's proportional to the square root of n. N is just a number, but we have to put in a phase. Okay, so there is also a phase. And just to be clear, if I write out what psi star is, that would be root n e to the minus I phi of r. And you can see now that psi star psi indeed equals n, because the e to the I theta and the e to the I minus theta will cancel each other out. Okay, so this phi of r is a phase. Okay. Very often we think of phases as not being very important, but actually in terms of the superconducting wave function, there can be a lot of meaning attached to the phase. And indeed, this is a way of, we'll use that, say, in the third year to look at superconducting tunneling devices where the phase will become critically important. Okay. Right, so now we have a wave function that we can work with. It's very fairly straightforward wave function, but we can now think about computing some properties from this. So I'm going to need to just switch over to my whiteboard, and we need to do some derivations. We need to look at how to include magnetic fields in quantum mechanics, because that's a little bit of chunk of knowledge that you haven't had yet, I think. So I just need to spend a slide looking at that. And then we'll go in to see how we can use this wave function and Maxwell's equations and wind up understanding the Meissner effect, but actually getting some insight into the screening currents that run in a material to give rise to the Meissner effect. You've got some blank pages in your lecture handouts in case you want us to copy what I write, but about 5 slides in, you'll see that I've actually provided sort of clean versions of all my derivations. Okay, so we now need to do an aside on magnetic fields in quantum mechanics. Okay, so I'm going to define the magnetic vector potential. I'm going to call that A. Okay. And what we will find is that the magnetic field B is equal to the curl of A. Now, we should compare this with electric fields, because remember, the electric field is given by minus grad phi. So this is, phi here is a scalar potential, okay, one number at each point in space, but A is a vector, okay. So this is why, so the scalar potential is for electric fields and the vector potential is for magnetic fields. We haven't come across A in electromagnetism so far, but it turns out that when we need to put magnetic fields into quantum mechanics, it's actually much easier to do this in terms of A than it is in terms of the field B. So that's why I need to introduce A at this point. Now remember that the scalar potential is not unique, because I can replace phi with phi plus a constant, okay, and this doesn't change E. Okay. What about A? Well, I can replace A with A plus grad F, okay, and this doesn't change B. Okay. Now, why is that the case? Well, you need to recall, and we did prove this with Simon Benjamin, that if I take the curl of a gradient function, this gives me 0. Okay, so a gradient function has no rotation. Okay, so its curl is 0. So there's a prescription in quantum mechanics for working out what happens when we want to formulate things in terms of a magnetic field. So the idea is that in a magnetic field, we replace the operator P, the momentum operator, so we replace P with P minus QA, okay, and this is what's often known as the canonical momentum. Okay, so if I want to work out, for example, how the kinetic energy changes in the presence of a magnetic field, I'd replace P squared with P minus QA all squared, and that would work through. Okay, so that's a little bit of background that we needed. Okay. So something else we need to know a bit about currents now in quantum mechanics. So we're going to think about current. So in quantum mechanics, the current, which is really just the flow of electrons, actually this is going to be the current density. Okay, the current density is given by J equals Q over M psi star P hat psi. Okay, but we want to do this in a magnetic field, but we know how to do that because in a magnetic field we just replace P with the canonical momentum. So if we do that, we'll get J equals Q over M psi star P hat psi minus Q psi star A psi. Okay. Now there's just to note something here. A will commute. It's just a vector. So I can quite happily just replace this with A psi star psi. Okay. Now I am going to do this for my superconducting wave function. So recall, first of all, recall that P hat is equal to minus I h bar grad. In 1D that would be d by dx, but we're in 3D. And the other thing is we've got a superconducting wave function, so psi is equal to the root of n e to the I phi of r. Okay. So I'm going to need to know how to do, so what I'm going to do is pop this into this. I need to take this wave function and pop it into there, given that this is P. Okay. So I'll need to be able to work out grad acting on phi. Well, that will just be equal to the square root of n, because that's a constant. The differential is going to bring me down I. I'm going to get my e to the I theta, and I'm going to get the differential of the phase. Okay. Now, recalling that psi star psi is equal to n, I can now plug everything in, and J will be equal to Q over N over M of H bar grad theta minus QA. Now, you might just want to pause the video at a moment and just see if indeed, if you pop all those terms in, that is what comes out the other side. Okay. Okay, so having done that, our final step would be to take the curl. And if we do that, we will get the curl of J and I'm going to get my constants. Now I'm going to get two terms. I'm going to get the curl of A with all of these constants out the front, and I'm going to get the curl of grad theta. But remember that the curl of the grad of a scalar function is 0. So actually I'm just going to get this term. Okay. So if I do that, I will get minus n q squared over m curl of A. But hang on, curl of A is B. So this is minus n q squared over m times B. And remember that I've used the fact that the curl of grad theta is equal to 0. Okay. Now, what is this equation that we've derived? So we have just derived that the curl of J equals minus n, which is the supercurrent density, q squared over 2m b. And this is what's known as the London equation. And the London brothers came up with this in 1933, not via quantum mechanics like we've just done. They actually just almost assumed that this was true. Okay, so they knew that this would have to be true in order for the Meissner effect to be the case. They believed the Meissner effect, so they came up with this equation. So this equation is valid, and we can derive it, but we've done this now on a quantum mechanical basis from the predictions of BCS, rather than just assuming it to be the case. All right, so we want to understand really some of the consequences of this. It will be helpful to define a parameter mu naught lambda, and I'll define it this way. If I say that mu naught times lambda L squared is equal to m over n q squared. Okay, that seems a bit odd, but it will become apparent later on. So lambda of L is a parameter. Okay, so I could write that original London equation in a slightly different way, just rearrange it. I could say that B is equal to minus mu naught lambda L squared curl J. Just move things around onto the other side. But let's remember a few things from Maxwell's equations. So Maxwell's equations say that the curl of B is equal to mu naught J. And another Maxwell equation is the Gauss's law, div dot B is equal to 0. It's very rare that that's actually a useful equation, but we are about to use it. There's another equation that's true. It's not a Maxwell relationship, which is that div dot J is also 0. And you might want to think about, again, what does the divergence mean? It's about the amount of net flux of something flowing through a closed surface. Well, a current can't, the current here has to flow. If it flows into a surface, it flows also out of the surface. Okay, we can't lose or destroy current in this case, so div dot J is also going to be 0. Right, so let's take the Maxwell equation. Let's call this M1. And if I take M1 and take its curl, all right, that will give me the curl of B, okay, is going to be equal to mu naught curl of J. Well, hang on, I know what the curl of J is, because that's the London equation. So I can sub in from the London equation, and I would get minus B over lambda L squared. Okay. Now, what do we do with curl of B? Well, we can look that up, and there are some nice identities, and here's a useful identity that's general for any vector, and it's this, okay? So we can replace the curl as the gradient of a divergence minus del squared, the Laplacian, okay? Well, hang on, that is equal to 0 from a Maxwell relationship. So in other words, all we've got left is this final term here. Okay. So if I just use this space up here, what this means is that del squared B is equal to B over lambda L squared. So it's a nice differential equation that the magnetic field in a superconductor must obey. Now, with a little bit of extra manipulation, we can actually show that the current density also obeys essentially the same equation. Okay. Right. So why does this help us with the Meissner effect? So let's just recap. Let's focus on the B part of this equation. So del squared B is equal to B over lambda L squared. Okay, we'll call this equation 1. Now, we're looking for, we're going to have a fairly big bit of superconductor. We're going to imagine that if there's a B field in it, it's uniform. Okay. So if we assume B is constant in the material, then this must mean that that the del squared B is equal to 0. I mean, if I differentiate a constant, I'm going to get 0. Okay, but from equation 1, the only way that del squared B is equal to 0 is if B itself is equal to 0. So the only constant field in a superconducting material is 0 field. Okay, and this is the Meissner effect. Okay, so this is quite powerful. All we've really needed to assume here is this idea of a kind of rigid bosonic wave function. Okay, that you know was uniform in the material, and that was a sufficient assumption that when we follow the electromagnetism through, we get the Meissner effect. Okay, but you may be asking a question now, which is, what about if B isn't constant? Okay, so in other words, can B vary? Well, we've got a differential equation, equation 1. We can try and see what would happen. Okay. So I'm going to need to set up a situation. Okay, so let's consider a slab of superconducting material. Okay, so here we go. That's my slab. So this side we're going to have our superconductor, this side we're going to have a vacuum. Okay, and we're going to apply a magnetic field B that is in this way. Okay, so here is B, and B we're going to look for the variation in B as we go inside the material. Okay, so let's define x, okay, as a coordinate which tells us about the distance inside the material. Okay, so we're trying to solve the equation del squared B equals B over lambda over this. Okay. Now we're going to be looking for, so B is going to change as I go into the material. We expect that, B outside here is B0, for example, and then inside the material, well, we know deep inside the material we expect B to be 0, but the question is, what is B in this region here? Okay. So we're looking at how B is going to vary with X. Okay, we're assuming there's no variation with Y and Z, and so the del squared operator just becomes the second derivative. It becomes d2b by dx squared, and that is just equal to b over lambda L squared. And this is a straightforward differential equation. Okay, we would look for solutions that look like e to the mx. I'm going to get two solutions. One of them isn't physical because it diverges as we go into the material, and the solution that we would expect here would be that b of x is equal to b naught, so that's the field outside, e to the minus x over lambda L. And remember that lambda L squared was equal to m over mu naught n q squared. Okay, so you see now why I introduced lambda L early on, because it's actually a decay length. Okay, it characterizes the decay of the magnetic field into the superconducting material. Okay, right. Let me just explore the last implications of that. So I will just write out that solution again. So we said that b of x is equal to b naught e to the minus x over lambda L, and that the lambda L squared is equal to m over mu naught n q squared. Okay, and we know what so lambda L we call it the London penetration depth. And typical values might be the order of, say, 200 angstroms. Okay, but if we could estimate, say, for example, the number of Cooper pairs in the material should be equal to sort of half the electron density, half the number of valence electrons, and we can put numbers in for the other things, and that would enable us to estimate what this distance is. So what this means is if I try to draw a little graph. So this is B, and this is distance into the superconductor. So maybe initially we've got B0, so we're in the vacuum, we're coming out here, and then so this is superconducting and this is vacuum, okay, and then we're going to see an exponential decay. Okay, so the magnetic field, and this distance here might be lambda L. Okay. So what we're saying is that actually these superconducting materials are not perfect diamagnets, in that the magnetic field does enter, okay, but it enters only in a small skin region, the depth, the order of a couple of hundred angstroms, okay, and it exponentially decays into the material. So as long as our object is macroscopic, is fairly big, the B field will be 0 through most of the bulk. The magnetic field will just be confined to this small region around the surface. Okay. A very interesting question might be, what if I had a sufficiently thin film of superconductor so that it was less than the London penetration depth? That's a question to perhaps discuss in tutorials. Okay. So one other thing is we showed that the current obeyed the same differential equation, and there's a relationship between the current and the magnetic field B. So what would the current density look like? Well, it would be exactly the same, that j of x is equal to some constant e to the minus x over lambda L. And so what we've got is we have these superconducting screening currents that are running around the outside of the material. It's those screening currents that are cancelling out the applied field and ensuring that I have no magnetic field inside the center of the material. Okay, but they're confined to this small region around approximately the London penetration depth around the around the surface of the material. Okay. So just to summarize, we've gone back from our superconducting wave function, and we've been able to understand some of the magnetic properties of materials of the superconducting state just based on that superconducting wave function plus some of Maxwell's relations. So if I just switch back to my presentation. So as I noted, the slides here are just the neater versions of what I've just gone through. So I'll just quickly click through those.